towards a modern network, sorry. Pascal Bélanger, and from University of Ottawa, and Mike Tyson from Aruba. It's a half-and-half presentation for Wi-Fi. Thank you.
C'était vite, ça. Oh, jeez. I'm just gonna get my notes handy. Oops. Where's Mr. Frank Pat something? Just give me 2 seconds. Oh, that is awesome. Pas la règle. Can I borrow your laptop for 2 seconds? Sure. Thanks. So I can't get my notes to come on, so I'm gonna multitask. There's a special key to get the USB. No? So, Mr. USB, where are you? Should just pop up under just under my computer. That's still installing drivers. Installing drivers for it. Yeah. Well, hi everybody. So I'm Pascal Bélanger. I've been working here for the University of Ottawa for 8 years. I'm a network specialist. So I've worked on tons of projects for the university, some from campus re-architecture, so what I'm going to talk about today, to data center re-architecturing, to also cloud infrastructure, firewall migration, VDI infrastructure, just to name a few. So today we're going to talk about small steps towards a modern network. So the topics we're going to cover, first it'll be our past infrastructure, what it looked like, how it worked, the topology that we choose to go forward with, the districts, the way we curved up our infrastructure, the actual physical network, our physical topology also, the address plan we're going to be using, or we're currently using, our security layer, the roles, our private cloud, and our network by the numbers. So this is a plank. Some people would find it really pretty, and some, but for network design, it is quite flat and imperfect. So our past network resembled a lot the plank. It was really, really flat. We did leverage VLANs, but it would be VLANs that would be spanning from left to right, from north to south. So a VLAN could span the entire campus. So for us, broadcast storms and spanning tree loop would be our worst enemies. One spanning tree loop could render the entire infrastructure unreliable and offline. So we had to readdress this to be able to at least deploy voice over IP and wireless infrastructure. So we had to rethink our foundation. So we went with, sizing is different. So sorry. So we went towards the good old trusted and tried hierarchical topology. So we went towards the hierarchical topology, but we also leveraged the VSS, Cisco VSS technology. So for us, we're using VSS at the core and at the distribution level. So basically, it combines, it allows us to use two 6500 catalyst switches as one. So it cuts down on the management, makes it really resilient, and also offers a faster convergence time. So in this scenario, you don't really see it, but physically you'd have two core switches, then two distribution switches, and then you'd have your typical access layer. So in this, it'll be 6500, 6500s, and at the access level, we do have a mix of 2960s, 3750s, 4500s, and also 6500 at the access level. So this was the topology we went for. So we divided our district to better allow us to control security and also utilization. So the actual carve up of the districts is based majorly on density, population density, also on the underlying fiber optic infrastructure. So for every district, we have a pair of distribution that feeds those districts. And from those distributions, we feed the access level. So one district, if it has a problem internally to itself, it doesn't really affect the rest of the campus. Also, we match I'll talk about this further on, but we've matched the IP address scheme per districts. So growth-wise, we're quite covered on that scenario also. And also we can even underlay the IP version 6 right on top of the IP version 4 scheme. So again, it allows us like rapid deployment of IP version 6. I'm just gonna check really quickly here for my notes. Sorry about that. Aha. Okay. Okay. So from here, this is our typical physical topology. So we choose the hierarchical network topology, but also we approach it more on a module base. So we've created different module to so if we ever need to grow, add like let's say a district, it is just like a cookie cutter. So you deploy your distribution, and your I'll be able to say it, your distribution and your accesses, and then from there you redeploy the same IP scheme and everything. So for us, we have 4 major modules. So we have the district module, which is the one that feeds the campus, the faculties, and like just the underlying community. And then we fall in the data center module, the edge module, and the campus services module. So the data center module is where we have our corporate applications, all the services that a teacher uses when teaching, and the students when they need to access their files and everything is stored basically in our data centers. So this is the module where we use Nexus technology, and where it offers us resiliency, convergence, so cut down on the cost there, and also has a I'll be able to lossless data connectivity. So and then from there we have also the edge module, which is the edge of the campus network. So this gives us access to the internet. Also our internet presence. This is where also our e-commerce would sit. So if you think about it, all traffic that comes from the internet or goes towards the internet has to hit the edge. So no actual traffic can go from the internet directly to one of the other modules. It has to be filtered and goes through the edge module. And also certainly our firewalls, we have firewalls there protecting us between the internet and the rest of the campus. And it doesn't show there, but we also have campus services module. The campus service module is the module where we have all our voice over IP controllers, our wireless controllers, and our DHCP and DNS servers. And those services are distributed on different locations on the campus. So it's totally reliable, resilient, and also well, it's resilient by the fact that if one fails, the other component is still active and continue working. Also, it makes them closer to the actual people that are using it, so it's faster response for the users. From here, we have the IP address plan. So this is the onion, so I like to call it, represents our IP address plan. The plan provides scalability, flexibility, and security to the networking and infrastructure by the means of private and public address space. It allows for a more controlled segmentation between the private and the public networks, enables the use of roles. For example, University of Ottawa web page would be using public IPs. But HR and finance application would be using private IPs. We have implemented security layers in order to provide different levels of security based on need and to address user requirements and sensitivity of data in each layers. So the 4 layers are the internet, the edge, the intranet, and the restricted zone. The components of some layers are quite straightforward, such as the restricted zone, which consists of the corporate database and our management networks. While the intranet zone consists of university applications and intranet web servers. The public zone, well, we call it the intranet zone, is where, again, we have our e-commerce apps, our guest access, and the internet access. The security layers. So the intranet, we find a grouping of security layers that contains roles. The 2 groups are the trusted users and the devices. Here you can see an example of roles that we have defined. So typically, you'd have your IT staff, your admin staff, professors. We also have labs and students. And in the device layer, we have IP cameras, IP phones, printers, clocks, and for our one card system, we have a layer specifically for the one card systems. So the roles that we have defined are the following. So the beauty of roles for the university is that users that are attributed the role of IT staff, for example, have access to applications, services, and resources that only accessible to the IT staff. If the user moves to a different building or campus and connects to a wall plate configured for IT staff, he will have access to the application, services, and resources that he needs. So we're leveraging the MAC pools out of our DDR infrastructure, which is BlueCat. And basically, a MAC address is configured in a MAC pool, and that MAC pool is attributed to a VLAN. And let's say a user comes in an office or something, plugs in his laptop, and he's not configured for that MAC pool, the user is not getting an IP. But if he's smart enough, he'll probably launch Wireshark or something and start sniffing and sees, okay, this is this subnet. Goes in, configures a static IP. We're leveraging also DHCP snooping and ARP inspection. So basically, if the switch never saw a DHCP offer for the statically configured address he gave himself, the switch will drop the packet because he's configured to do that. Okay, for us. So from here, or not from, well, yeah, in the distant future, we're planning to move towards a more dynamic approach. So basically, a user would plug in his laptop in a port. He'd get credentials. He'd have to supply credentials. Based on those credentials, he's going to be attributed the role that is configured through Active Directory. And from there, he's going to have access to his resources. But we're also aiming to do the same thing at the wireless and at the remote access level. So either like if he's at home, he's on campus, working in a hotel, he'll have always the same field or level of access. So from here, we have the cloud. So for us, the cloud for the infrastructure, the network infrastructure team, we try to push towards more a private cloud compared to a public cloud because it offers, we have more of a control over the, especially the bandwidth, the utilization. We can custom the QoS so that the experience for the user is more enjoyable compared to an experience on a public cloud. We don't have control over once it goes to the internet, we don't have access to the internet itself, so we can't really control on that side. And also on a private cloud approach, we do also have control over the fabric and the storage subsystems. So we have more control. So I said it like a couple of times, but it keeps us in control of the actual infrastructure itself. And last but not least, this is our network. Oh, there you go. This is our network by numbers. So today we have 3,158 network devices that feeds 41,600 wall plates. And out of those are 3,158 devices, 2,700 are wireless access points. And the wireless, the wall plates provides connectivity to 22,000 devices. From there, 1,200 are managed printers. From the access points, every day, we provide wireless connectivity to 38,500 users with a peak of 18,499 concurrent users. All of this to sum up to a lease and use of around 60,500 IP addresses per day. Anybody has any question? Oh, yes.
So you said you give out IP addresses to your MAC address pool?
Yeah.
Do you have a MAC address in all devices?
Not entirely. So right now, the MAC pooling is used for the wall plates itself. So everything that's wireless, it's all dynamic ranges. But everything that is on a wall plate, we're in the process of flipping everything to VLANs that have MAC pools.
You use static before that?
Yes. So initially, the other system we used to have was a pure registration. So you really had to register your MAC address, but you had to we had to provide static subnets to people. Now we don't really care about what subnet you're actually on. We just identify subnets of all the same nature, and then we attach MAC pools to them, and we pre-configure the wall plates. So now we're still statically assigning VLANs to wall plates. Eventually, we want to get to the approach of we don't configure the VLANs at a wall plate. We just, based on your credentials, we assign the VLAN, and that's it. Oh. Yes. The 38,000, this is total throughout a day, but the 18,000, let me go back.
Actually, they are the unique users.
Well, this is unique user per day, and this is unique user at a particular time. This is our peak period, but this is unique users throughout the day. So you won't have the same MAC address show up in this number.
Unique devices.
Yes, yes. Yeah. Yes, your device is not users. Yeah.
The Wi-Fi was 6.
Yeah. Okay. Well, I'll let it to Mr. Mathieu. or Matt.
Thanks.
So, yeah, I'll
I don't
set
know
it up
where.
for you. Boom. So he just put it on the boom.
So, Khalil, if you want to jump in anytime to kind of talk about what your plans are, I know a little bit, so I'll include them.
If there is any question, I will
Sure.
answer.
Is that good?
yeah.
Oh, cool. There you go.
So it's actually been 10 years ago this month that I installed my first Roomba network.
Oh.
An anniversary, so it's I hair that. And it was 802.11b. That was the first generation, obviously. And now we're on the cusp of the 802.11 AC. So it's kind of the third major technology transition. University of Ottawa is our first, I think, customer in Canada deploying AC. AC is in this room for anyone with an AC client or connected to one of the two access points. That's an 11 AC network. So it's real, it's up and running. And from a throughput perspective, in our early tests with some clients that aren't yet available, we're seeing 850 megabits per second of actual TCP bidirectional throughput. So it's a pretty screaming fast technology. And we really kind of see it. If you look at the numbers that were just presented, the wireless usage is obviously going up and up and up. And we really see 11AC as being that technology allows us to make the edge entirely wireless in a lot of cases. So there are a couple of different innovations, I'm going to say, behind 11AC to begin with. The first one is just the raw hardware. But the hardware is all standards based, and from an access point perspective, while I think it's pretty fine AP, really it's the software that allows us to get a lot of these speeds out of it, and that's something we coined as client match. All of the vendors in the wireless space have been working for the better part of a decade now on optimizing the wireless experience from a connectivity perspective, and that includes how I manage the AP, so I'm not taking and manually channel the power, but it also takes into account how I what's this?
It's the thing.
Oh, like am I supposed to use that? Good. It also includes how the client experience is managed. Finally, it includes the presence of applications on the network. So I'll kind of walk through what the latest generation of RF management is all about with this specific client match technology. And even though it was developed with 802.11ac in mind, it works on existing 11n networks. So we'll talk about that. But essentially, the APs that are up there, this is I think the first production network running. We're providing the first generation of 11AC, which is 1.3 gigabits per second of a data rate, which translates into roughly about a gigabit of throughput on the back end when you leverage both radios. So AC as a technology is a 5 gigahertz only technology. What this means for education is we're going to see a fairly rapid shift off of 2.4 gigahertz finally, thankfully. The industry numbers are somewhere around 70% of all new clients shipped starting this holiday season are going to be AC capable clients, which means they have no need for 2.4 gigahertz. And we'll see kind of that Christmas or after Christmas rush of clients into the network. And we expect the 5 gigahertz to have a pretty significant boost in utilization then. The other thing this means is the client counts, while they may not be connecting to 11AC access points, the 11N is obviously a backward compatible component of that, and they'll be operating at 11N speeds. So those 802.11n access points that everyone's been deploying for a long time are finally going to get pushed a little bit more, and that 2.4 gigahertz band is going to start to become abandoned pretty quickly. The other major innovation in 11AC, aside from kind of the raw radio statistics, really is this technology around implicit beamforming, which is standards based. So this is from a capacity standpoint, basically giving us a much better signal noise ratio in the network that drives up higher channel utilization and higher capacity from the overall spectrum. We're seeing that as probably the biggest benefit of 11AC out of the gate. We don't anticipate people running it in 80 megahertz channel widths. We only have 5 channels available, which when you talk about a lecture hall, for instance, if I've got to serve 1,000 clients, we typically get a better aggregate throughput out of running 40 megahertz channels. We are running 80 megahertz channels in here and 3 spatial streams 802.11ac as a standard does have a long way to go, though. It won't be until like the 2015 to 2017 range that we'll see the 11 AC standard fully utilized with the 8 spatial streams that the spec calls for. But the exciting part in all this is this client match technology, which essentially works in combination with 11N access points and 11AC access points, and proactively manages the air from a layer 1 through 7 perspective. If you think about the air being a data link and just a layer 1 technology, really being able to take and utilize information in a contextual manner across layer 4 through 7, layer 2 and 3 to manage how we use L1 is what this client map is all about. And we want to be able to take and load balance clients in a much more intelligent way. Historically, load balancing was always about putting more APs in and wait for a client count threshold to be hit and then start pushing clients around. So if I've got 100 users walk into a room with 2 access points, I potentially end up with 50 clients per AP. And that was interesting, but that really didn't take into account spectral utilization and ongoing applications that were on the network. And as we've seen the wireless numbers jump up and up and up, we deal with more and more density. And when we looked at how we tackled density historically, we would typically add more access points. Adding more access points would certainly provide us more capacity in the network, but it didn't always result in a better user experience. And the reason for that is we have clients potentially connected to suboptimal access points. So if clients would roam throughout the network, we could run into scenarios where a client would perhaps be right under an access point, but connected to an AP across the hall or in another room. Now, the biggest drawback to this is the client is transmitting a slower data rate, and slower data rates consume a disproportionate amount of airtime and lower the throughput available for all clients on the network. So the first step in taking this client match approach was if I've got clients that are kind of connected all over the place as they've roamed throughout the hallways and switched between classrooms as classes changed, I could end up with a network that looked a little bit like this. The goal of client match was basically to take and analyze the connection at layer 1 from all clients and push them to the appropriate APs. So this is done using a couple of different standards, 802.11k, 802.11b, and 802.11r. And it also uses some proprietary technology that we've developed to take and assign the appropriate APs and then gracefully hand those clients off. So with the layer 1 optimizations, we can start to end up with a network that has the clients connected to their closest access point. Now, this in and of itself basically saves us a lot of channel utilization because we're keeping the data rates of the clients fairly high. The other thing this allows us to do is start to layer on additional technologies in terms of how we're balancing clients. So once we get the APs and the clients communicating in the proper fashion, where they're talking to their closest access point, then we have to take a look at layers 2 and 3 in the network. So from a 2 and 3 perspective, these APs are obviously taking and aware of the traffic that's happening on them in terms of channel utilization. So if we add more and more clients to the network, we would typically experience slower connections. When we have an instance where some clients are doing things like video or heavy file downloads, you can obviously have the spectral utilization on any given channel increase. When that happens, the overall throughput on that channel goes down, and we need to start taking and balancing clients from a utilization perspective, not just from a link perspective. So in this case, we're taking and analyzing the different applications that are running through the network and then adjusting the RF accordingly. So by seeing traffic like Link or like Skype or BitTorrent, being able to take an increased priority or adjust priority, optimize multicast video, or turn Bonjour traffic into unicast and route that properly. All of that is dependent on using this application awareness. At the end of the day, essentially what this comes down to is using that layer 4 through 7 knowledge as well and optimizing the air around that. So if I've got multiple clients on an AP that are streaming data or downloading video, load balancing those clients across their available channels is critical. But when we take a look at different applications that are perhaps more advanced, such as Microsoft Link that we're seeing, it requires a little bit more heuristics and a little bit more deeper packet inspection to determine what exactly is happening. we've built networks for a really long time around this concept of convergence. We've taken and we've took a voice network and a data network and we put it together and we run voice over IP on the wire. And then a few years after that, we took and we ran soft clients on our laptops and we had voice and data on the same device. And that's where that port-centric architecture of having a voice VLAN or data VLAN really started to break down. Now we're starting to see the highest grade of convergence, and that's at the application layer. I've got a piece of software that does voice, that does video, that does file sharing, that does chat and presence, and I've got that all in one stream. So being able to take and rip that apart and actually use that traffic inspection starts to become a lot more critical when we're managing the air. So if I've got clients that are connected, to a specific AP, and there's video going on and there's voice going on, perhaps I want to start splitting those clients up and using that application layer intelligence to push those clients to the least utilized access points allows us to keep a very high quality of service on the network, even in the presence of applications like Apple FaceTime or Microsoft Link. This is all a result of using intelligence that we can glean at layer 4 through 7 through deep packet inspection technology and contextually manipulating the air from a traffic shaping and a bandwidth and a client load balancing perspective. So at the end of the day, where we focus kind of at RF management out of the gate was always on that layer 1. How do I take and just plan my channels better and optimize that so I don't have to configure it? How do I take and set power levels so they don't create co-channel interference, and how do I mitigate co-channel interference if it does happen? But really kind of the next generation of wireless is taking into conjunction the layer 2, the layer 3, and the 4 through 7 information, using all of that together really to take and manage that layer 1 link. Do you want to add anything, Khalil, about your 11AC deployment? How many? Yeah.
I can add this bit what our plan.
Just your plan for
deploying. Yeah. So my name is Khalil. I'm the network manager. Before I worked a lot on the wireless on campus. On campus. Our plan right now, our campus actually it's mixed of ADG and N. We have a couple of buildings we already deployed N, but I would say half and half. So half now it's most N and half ADG N. So from our management tool, we were able to find which are the buildings that the high density, and most likely it's our center university, where the library, the university center, there where we have high density users. So our plan right now is like we have N actually right now there is to replace the access point N by AC in the library and the university center, and try to replace the old ADG by the N. So right now we have almost 3,000 because we just started deploying wireless and residence. As Pascal mentioned on his slide, we have 2,700, but this number will jump up to 30,208 access points because we have deployed wireless internet. So I would say actually we start those 2 years by our AC. We have 200s coming in also too for the site engineering building. That the first building will be AC. So I'm not sure if you have any questions or. Sorry?
Outdoor wireless AC.
Are you doing outdoor today?
Outdoor, okay. We have we started actually.
Okay, before you answer the question, repeat it for
The question was if you have any project to deploy wireless outside. Actually, yes, we do. We started actually planning to deploy wireless outside. I didn't have any right now, but in the summertime, I'm planning to install. The protection services approach us, and they found out that it's very important for them to have access wireless outside of the buildings. So we are trying to deploy wireless in the parking lot and some areas where students also sit outside. There are some green spaces where students gather most of the time. So we are attacking those areas.
I have to ask, how is Wi-Fi a safety and security issue?
Well, Sorry, how Wi-Fi?
Why would you deem Wi-Fi to be worthy of a safety of life service? I don't understand how it would be.
Protection services. Why are they?
Oh,
Why do they want?
I might be able to answer that.
Yeah.
The reason is that they have. It's really not about safety issues. It's really about the ability to interact better with the net.
It's the
They also
parking.
have cell phones and everything else.
I will mention the parking department is part of the protection department. So when I say protection, it's only the parking department. The parking department, as Pierre mentioned, so they go between the parking and check the plate and check the passes if they are valid. So usually they do it via a PDA or an iPhone. So that's why they need it.
And the second thing is, when there is a crisis, the actual cell phones and everything, they're over, the density is way too much. People are using them to the ability to actually use your cell phone. Whereas the Wi-Fi is just reserved for the local area here and it's actually more available.
Any other question?
So you're saying 80 megahertz channel are being used here. So
It depends on what channel width you're using. If you're using 20 megahertz channels, you've got 24. If you've the question was how many channels are available.
you mentioned you're using 80 megahertz.
Yeah, we've got 5 channels to play with at 80 megahertz.
So you have 5 antennas.
Yeah.
In 5 hertz.
In 5 gigahertz. 811 AC is a 5 gigahertz only technology, so it forces the use of 5 gigahertz, which is really nice from a client perspective. But 80 megahertz channels is the widest it goes in the first spec. It will approach 160 megahertz channels, but we don't really see that being a technology for the enterprise. That's really a technology for the home. The 80 megahertz channels is going to be the widest you'll see in education or general enterprise. So just really quickly before we wrap up,
We
another.
have
Oh,
another question.
So all the new buildings AC, AC.
We have coverage 100%. Our campus is fully deployed right now, but we are trying to upgrade our hardware, our access point, the legacy 1 AVG to N, and now to AC. So the first building is, as I mentioned, is a engineering building that will be AC, but right now we have AVG on it.
Like ARC, the new building there.
The new building will be, like any new building will be AC.
And just lastly, because we've seen a lot of education, this is purely a feature or technology that's built out of education, and they've implemented here at the University of Ottawa, is something we call air group. So we've seen Apple kind of come in massive waves, and what they've created from a file sharing and a discovery protocol standpoint is this technology called Bonjour. So I think everyone's probably familiar with Bonjour. But Bonjour, being designed for the home and working on flat networks, really wasn't discoverable across large campuses. So if I was on a VLAN that existed in this room, but my Apple TV existed at my office, I couldn't necessarily connect to that because I didn't have layer 2 connectivity. So the industry rapidly comes up with ways of tackling that and develop Bonjour gateways, so ways of taking and snooping multicast, converting it to unicast, and routing across VLANs. That was an interesting stopgap, but then we realized that created a lot more problems than it actually solved. Now I was taking and spreading my Bonjour everywhere, and if I turned it on, I would have lists and lists and lists of all the Apple devices on my network show up for everyone to use. So leveraging that context awareness, being able to take into account who the user is, what the device is, and wrapping firewall policies dynamically around that, we said, wouldn't it be cool if we could take and group these devices and group these users into buckets that were allowed to see these multicast Bonjour conversions. So essentially, what this allows us to do is perform this multicast conversion to unicast and route it across the entire network, but it allows us to intelligently assign devices to groups. And I can have a shared air group where a teacher may be able to access all of the Apple TVs in the classrooms that are just assigned for the teachers, or where a location-based air group is defined, where only in the specific auditorium can the devices see that. So rather than have this kind of binary on the network or off the network approach, where either all of the Bonjour capable devices are visible or just those devices in your VLAN, air group basically allows us to only make the devices that we want to make available to specific users and share them based on either personalized air groups where one person can see their Apple TV no matter where they roam on campus, shared air groups where devices are allocated to specific roles of users, or location-based air groups that allows devices in proximity to one another to see those advertising messages and be broadcast. So now we kind of get the best of both worlds. We make Bonjour routable everywhere on the network, and Apple TVs and AirPrint capable printers are all visible. But we can contain those messages to only the devices that need to see it through this technology. So that's being implemented today. Actually, it's running at University of Ottawa, and then the groupings are taking in and being built out now.
We have time for one more part. Any client software?
No. No, the question was, does Aruba Client Match require any client software? And no, it's purely client independent. Clients that support the standards of 802.11k and 802.11v are helpful, but not necessary. And if they're legacy clients, we have other methods that can take and match those clients to the appropriate APs. Thanks.
Thank you very much.
If anybody wants to come by our booth, I'm Bruce, I'm the country manager. If you got any questions about AC or the client match,